problems with the homework, right? So we'll go through that now. So let's just go. This is our table for error propagation. Add this person again. All right. Yeah, so some persons are saying that they're having problem with the error propagation. But remember, we have our sum rule. This is for errors, right? Difference rule for errors, product rule. Whenever there's a product, right, it's the same form, right? We have our uncertainty over A, delta A over A, delta B over D over B. Same thing for quotient. If we're dividing two quantities, it's the same thing. And for the power, right, you will find that you multiply the power by the uncertainty. All right, so this was our question from last class. I'm going to need you to help me, right? So we have here that with a stopwatch, you time it take the time it takes for a friend, right, to run, right? And you see that's 8.5 seconds. And the human reaction time is 0.25 seconds. What does that 0.25 seconds represent?
Sorry, that'll be uncertainty, sir.
Right, so that would be the uncertainty. Yeah, you can be more confident, right? That was a reaction time of, let me see, that's 10 seconds. So this class has an uncertainty of 10 seconds, right? So the the time it takes for the friend to run 50 meters, right? And they run this in 8.5 seconds, right? That's fast, but not. We can say this person is not that an athletic person, right? It runs at 50 meters. And now we see the 0.5 coming up here again, our uncertainty again. Now, if speed is equal to time distance over time. So speed, distance over time, right? Then we find our speed. So what would the speed be here? What would you have at the top? What would you have at the top here for distance?
50 meters.
So 50 meters, and we have time, right?
8.5.
8.5. So let's get our calculator. What is that?
5.88.
All right, so we
Meters
all
per
getting
second.
5.8. Are we all getting that? I need one more confirmation to ensure that we're on par.
Yes, sir. Same thing.
All right, so 5.88, that's good. 5.88 apples meters per second. All right, now we're going to get our relative error in speed. Now, before we can calculate our relative error, remember we spoke about finding the uncertainty first. So the relative error, right? We have to use our calculation, our rules here to find our uncertainty. Now, that would be delta S, right? Delta S, is that correct? This would be our uncertainty or our error, right? Our error
Yes,
for speed.
sir.
Exactly. Now the formula, let's go back to our product rule. We'll take out the product rule here. Is delta R over R equal delta A over A plus delta B over B. So we do the same thing. Delta S over S equal, what goes here? We have the other quantity here, right? So what do we have here? All right, so Apparently you're not hearing me. Probably it's my internet. Let me go again. We have the product rule, right? The product rule meaning two quantities are being multiplied by each other, right? And we have the quotient rule here. These two take the same form, right? So in this case, my apologies, we would use the quotient rule, right? The quotient rule. So R equal A over B. R equal A over B. So therefore, you would have delta R over R equal delta A over A. Remember, A is in our formula here, and delta B over B. That's what we would have. Now, for this particular question, we're trying to find our error. So therefore, we have delta S over S. What would we have here? I'll do the second one. Delta D over D plus, what's the final one?
A time.
Right, so I need, what should I put here? It will be time, you're correct, but what exactly will be put in
Delta
form?
T over T.
Right,
Delta T over T.
that's what I've been waiting for a long time. Now, the next step is to find delta D over D. So what is our delta D? What is this up here? From the question.
Changing it.
From the question, right? Are we seeing this? Hello? What would be our
Yes,
delta
sir.
T? Delta D would be what?
0.5.
Are you all seeing that? 0.5, right? Over the, I know this is new, right? I know this is new, but let's give it some time. We're going to do a lot more practices in this, all right? And then D would be what?
50 meters.
Exactly, 50 meters. And we'll do the same thing for delta T. So delta T would be what?
0.25
0.25 over
over 8.5.
over 8.5. So let's do the first one, 0.5 over 50. So much?
0.01.
Exactly, 0.01 plus 0.25 over 8.5.
0.02 or 0.3.
Right, so 0.03 because we can round up. We have a 0.029, we can round it up to 0.3. And we put this together, 0.01 plus 0.03. What would we get?
0.04.
Exactly, 0.04. Right, so I like how we are now participating. Right, I don't know what was happening earlier. Right. And what is our S, or our speed?
5.88.
5.88. Are we all seeing that? If you're not seeing that, stop me, please. I send a message in the chat. Sir, that does not make any sense, right? We want to get delta S on one side, so what do we do here?
You carry it over.
By, or we carry it over?
You multiply.
Exactly, so we multiply both sides by 5.88, right? 5.88. These two cancel. We have delta S equals 0.04 times 5.88. Are we all seeing that? Are we clear?
Yes.
All right, so this two part is clear. How are we doing, Oshin? Oshin, are we clear? All right. Simpson, right? I just want to ensure that we're all understanding.
Yes, sir.
All right, so Simpson is clear. Whittingham, are we clear?
Yes, sir.
All right, Campbell, do I have to go through and ensure that everybody's clear? Campbell, are you clear?
So everybody good, man.
All right, everybody's good. I hope. If you're not, please stop me. All right, so what's the final delta S?
0.24.
So 0.24.
Yes, sir.
Mhm.
All right, 0.24 apples, 0.24 dumplings. What's our unit?
No MS.
Right, so meters per second.
Per second.
Right, so our final answer. The answer for 2. So this is 1. This is 2. Right. This is 3. Right. So our final answer should be 5.88. What's the next? What else should we write?
Plus or minus 0.24.
Exactly. Plus or minus 0.24 meters per second. That's your final answer. Right, your final answer. No, what is the fastest speed that this person can go according to our arrow? What is the fastest speed this person can go?
6.12.
All right, everyone is getting 6.12. All right, 6.12.
Yes, sir. Same thing.
Meters per second. And let me put, just not to confuse us. 6.12 would be the fastest. Right? And then what would be the slowest?
5.64.
All right, so 5.64. Are we all seeing that meters per second? All right,
Yes.
we missed out something here, right? Okay. Oh dear me. Relative error. The relative error meaning the fractional error. So this would be the answer for number 1. Right, the 5.88 plus and minus would be the answer for number 1. 5.88 plus or minus 0.2. Right, remember it's one significant figure. Right, remember we spoke about that? So it would not be 0.24. It would just be 0.2. All right, so make a note of that. Just one significant figure, plus and minus meters per second. And then our relative error would be delta S over S. Delta S over S, where we're relating the error to the actual quantity. So that would be, what would that be?
0.25.
Or 0.2, right? 0.2, one significant, let's put that one significant figure,
yes,
right? 0.2 over
5.88.
5.88. What is our relative error?
.03.
0.03. No, add on one more question to this, 0.03. Right? I'll add on one more question to this. What is our percentage error now? This is not in the question, but what is our percentage error?
5.
No. How do we calculate our percentage error?
3%.
Exactly. So our percentage error Alright. Let's see if I can find it. Where is it? Oh, it's not here. Oh, probably it's in the other slide. It's in the other slide, I think. It's not here right now. Right. I passed it. So the percentage error is our fractional error, fractional uncertainty, right? Or relative error, right? Can be either if you see a question asking you for the relative error or the fractional uncertainty, you know what we're talking about. It would be our fractional uncertainty multiplied by 100, right? Multiplied by 100 to represent the percentage. So the percentage error would be 3%. All right. Is that clear for everyone? Please stop me, right? If you're not understanding. All right. Remember, this will be posted on Google Classroom, so you don't have to write this. If you want, though, you could write it or after the class by going through it. I find when you write notes, it's much better. So you could write off what you're working out after the class to ensure that you get it. Don't wait until it's test time. You try and rush it and in your brain. All right, so for today, we're going to move on to scalar and vector quantities. Right, this is one of my favorite aspects of physics. Right, it relates to maths a lot, and we'll see that in a few. So each quantity can be categorized as either a vector quantity or a scalar quantity. The scalar quantity is a quantity that can be completely described by magnitude. That is a number and a unit. For example, masses, time intervals, volumes, and temperatures are all scalar quantities. If the mass of an object is 20 kilograms, this information completely talks about the mass of the object. No direction is required, no direction is given, right? Just the mass. On the other hand, if you're talking about force, right, or weight, we would attach some form of direction. Weight acts upwards, right? Weight acts upwards, right? I don't hear no one agreeing or disagreeing.
No, sir.
Exactly. So weight acts downward. So weight would be a form of vector quantity. So this is a quantity that needs both magnitude and direction to completely describe it. For example, a car is moving at a velocity of 60 kilometers per hour north, right? So we have our magnitude and direction. We did this from CSEC, so we're not going to spend too much time on this. Scalar quantities can be manipulated with rules of ordinary arithmetic, right? While vector quantities or vectors can be added and subtracted from each other and multiplied. But there are several important differences, right, that we must consider when manipulating vector quantities. All right, so as I said, a vector quantity talks about direction. So therefore, we must represent it on a diagram. Moving forward, you will have a lot of quantities you have to represent on a diagram, right? Some of them you will see are required by your syllabus. So it is an arrow, right? Usually an arrow from the origin of the Cartesian coordinate or coordinate system as shown in the figure below. Starts the angle here, starts at the origin, and it is displaced at the angle. We usually relate it to the x-axis, and this is your vector. This is how we write vectors, right? I'm not able to do this on the computer. So you might see just A, like vector A. I say vector A to show that it's actually a vector, right? It should look something like that. So the length of the arrow represents the magnitude of the vector. So if you have a vector or a force 1 Newton, it would be represented something like this, 1 Newton. But if we have a force of 2 Newtons, it should be represented something like this. All right, 2 times the size. All right. So the direction is specified by the angle, right? This should be theta that the vector makes with the x-axis. So usually the x-axis. We usually use the x-axis, not really the y, right? The standard is that we use the x-axis. So the magnitude of the vector is equal to the absolute value of A without any form of direction. No negative sign, absolute meaning no negative sign, just the raw quantity. That is your magnitude of your value. So are we clear on vectors so far? You can type in the
Yes,
chat.
sir.
Yeah? Okay, thank you, Tyrese. I need one more confirmation. You can type it in the chat. Yes, sir. Can you use the mic?
Yes, sir.
All right. So the components now, we move on to the components of a vector. Now the component of a vector is the effective value of a vector along a particular direction, right? So figure 1 represents a vector A, right? We see vector A again at an angle with x direction, right? So this is our angle relative to the x direction of vector A. Now, we want to find the effective value of the vector along a particular direction. So there might come a time when we need to find the value of, or the value of that vector, the effective value of that vector along the y-axis for a particular purpose. We want to know the total amount of force acting in the y direction of different forces acting. We can use the components of a vector. Right, so figure 2 now, figure 2 breaks it down a lot more. It shows the components of a vector A along the axis of a rectangular coordinate system. Right, so we have vector A there. Now we look closer and we see component AX and we see component AY. So if there was another force, so we had a force here, and let's say we had another force here, right? We had another force here. This is B, vector B, and this is vector A. There might come a time when we are required to tell you the total amount of force acting in the y direction. So we'll have to find the component for B, the BX component, or the BY component, sorry, BY component plus the AY component, which would give us a total amount of force acting in the y direction. All right, BAY, let's put that as BAY. So we want to find the force that is acting in the y direction. We have to find the components of each. So any vector A lying in the xy plane can be represented by this rectangular component AXY, right? AXY. And of course, they must match to the y-axis. This would be your actual vector, and then these would be the components. Are we understanding the concept of components?
Yes, sir.
All right. So to find the component on the diagram, you should find the projections of the vector along the axes, right, as we just said. So by means of perpendicular dashed lines. So we talk about these, right, these particular dashed lines, these we will match up to the different axes to find the components, right, to find the various components. So that is, you should drop a perpendicular from the tip of vector A onto each axis, right? So AX is a component of the vector A along the x-axis, while AY is a component of vector A along the y-axis. All right, so the magnitude of these components can be found using the trigonometry functions, right? We see this coming up back again not necessarily to haunt us, but to help us, right? To see them coming back again to help us to identify these. So we remember, so ka, to, right? Remember this?
Yes, sir.
Yeah, so this would be for sign, this would be for cost, and this would be for your tan. We're not going to use tan much, right? Because we're not comparing the x-axis and the y-axis coordinates. We're looking from the hypothesis, right? The hypothesis. We're relating the different components to the hypothesis. So you look something like cos ax. Let's go back, or let's bring out back that diagram here. We have a component A, we have a vector A, right? And we go from the tip coming down, and we start at the tip coming down, right? So this would be our AX, sorry, and this would be our AY. Now, if we want to find AY, you would use so, right? Opposite over adjacent. No, sorry. Let's start with X. Yeah. Let's start with X. Right, we have our angle here. And we want to find the AX. So AX would be the opposite. Remember, this is the opposite, the adjacent, sorry. This would be adjacent. We want to find X. So cos adjacent over hypotenuse. The hypotenuse, of course, would be A. And we want to find the adjacent, which would be AX. So that would be cos equal AX, which would be or adjacent over hypotenuse. Over the hypotenuse. And in order to find adjacent, we would basically transpose. So what would that give us? What do we do in this case? To find the adjacent. All right, quickly. We don't have much time left. How do you find adjacent? How do you find adjacent? Over here. Are you hearing me?
So let me always find adjacent.
Right, from this formula here, we want adjacent over hypotenuse. How would we find adjacent or make adjacent the subject of the formula?
So I put cos theta over 1.
Cos theta over 1? No, not really. We want to get rid of hypotenuse, right? The hypotenuse.
No cross multiply go, no.
Yeah, so it'll be, we multiply both sides by the hypotenuse, right?
Oh, yeah.
Right, multiply both sides by the hypotenuse. And these two would cancel. So we'll be left with adjacent times cos times hypotenuse. All right. And for the AY component, remember the opposite would be the AY. Opposite would be AY. So we'd have something like sine equal, it's sine theta equal AY over A, right? Or opposite over hypotenuse, right? And we want to get opposite on one side, which would be our AY. What do you do in this situation?
Cross multiply.
All right, so multiply both sides. That's good. I multiply both sides by hypotenuse. You would be left with sine theta times the hypotenuse equal opposite, which would be our AY. So is that clear for everyone?
Yes, sir.
All right.
Yes, sir.
So I'm only hearing 2 persons. Is everything okay?
Yes, sir.
All right. All right. Whittingham, is everything okay? And Simpson? All right, so I'll take that as a yes. Remember, if you have a question, please let me know. All right, so we now move to an example. Sorry. We now move to an example where we consider that the vector A is a force. It's a vector force with a magnitude of 20 newtons. And the angle, right? The angle that it is formed is 30 degrees. Angle that it is formed is from the x-axis 30 degrees, right? So let's try this one. Let us find first the x direction. So we start out with x direction. All right, now what's the next step? Which one of these do we use? So, ka or to, which one do we use? Hello?
Sir, go up, please.
Yeah, the slide, sir.
All right, for the x direction, which one do you use? You want to find fx?
Ka.
All right, so we use ka. So what would that be? Next step. What does it C stands for?
Cos.
Right, so cos theta. What's the next one?
Adjacent
All right, so adjacent
over hypotenuse.
over hypotenuse. Right? Now we have the value for the hypotenuse, right? What is the value for hypotenuse?
20 newtons.
All right, so we have let's equate this. So what is our adjacent from this particular diagram? What is our adjacent?
Fx.
Exactly, fx. Guys, be more confident. Thank you. All right, fx over hypotenuse.
20, sir.
Right, we were looking for the symbol, right? Symbol here.
Oh.
Yeah. It should be F, right?
Yeah.
No, we will go down and put fx here over as someone says, 20, right?
Yes, sir.
And we would have cos times what?
30 degrees.
No, not cos times 30. Sorry. All right, so cos 30. Sorry. Cos 30 degrees. All right, next step now would be to what? Let me write this properly.
Carry over 20.
Okay, and how would you do that?
Plus one.
Times.
So we times both sides.
By 20.
So let me do this. Cos 30 degrees. And we multiply both sides by 20. We multiply both sides by 20. These two 20s cancel, leaving us with fx, right? And this would be cos 30 times 20. Now, what is our final value for fx?
17.3.
17.3. Is everyone getting that? Right? One more confirmation.
Yes.
Yes, sir. 17.3.
17.3. All right, so this meeting is going to end in 17.3 what? 17.3 apples, 17.3 guineas. 17.3 what?
Newton, sir.
Exactly. 17.3 newtons. All right, so this meeting is going to end in less than a minute. So we'll pause and come back and then we'll do the y direction. Y direction, we're going to do y direction. So rejoin as soon as possible. We have less than 9 minutes for this class.